Method for visualizing and calculating angular momentum. Angular momentum is a vector quantity and angular momentum is denoted by the symbol vector L, and angular momentum is given by the cross product of position vector with the linear momentum. So we have this. So this is position vector, okay, and this is linear momentum. Now let us consider a particle moving in XY plane. So let us understand it with reference to this diagram, okay? This is X, this is Y, and let us take Z, okay, axis perpendicular outward to the plane of the board. So I'm taking Z axis, okay, which is perpendicular to the plane of the board and is directed outward. Now, as I said earlier, particle is moving in XY plane. So this is origin. So this is the position vector. And let us consider linear momentum, okay? P acting along this direction, and this angle is theta. So theta is angle between position vector and linear momentum. Now, in this situation, okay, the particle move in the direction of linear momentum. So we have this. This is to be noted, okay? Now, let us find the direction of angular momentum, and we use right hand rule, okay? We use right hand rule to find the direction of angular momentum. Now I am rewriting angular momentum in vector form. So we have this, okay? And this is the first vector, okay? And this is the second vector, and we rotate first vector towards the second vector in order to find the direction of angular momentum. Now let us consider right hand, okay? So I am taking right hand, okay? And I am keeping my finger along the direction of R. Let's say the black pen, okay, gives the direction of position vector R, and the pencil, okay, this gives the direction of linear momentum. So if I rotate, okay, the finger, okay, of my right hand, which is pointing along the direction of position vector towards the linear momentum, okay, towards the linear momentum, then the outstretched thumb of my right hand, okay, gives the direction of angular momentum. So for example, in this case, okay, we have this. Okay, then we find thumb, okay, thumb of right hand acting along Z axis. So we find angular momentum, okay, in this condition or in this situation. So we find when we rotate finger, which is pointing along the direction of R towards, let's say the position vector is rotated towards the linear momentum, we find thumb pointing in outward direction. So we find thumb pointing along Z. So this is one way, okay, to find the direction of angular momentum using right hand rule. Next, what we do is that let us redraw linear momentum, okay, without changing its direction at origin. Okay, so I am redrawing linear momentum with its tail at O, or we can simply push this linear momentum without changing its direction at the origin. Now what we do, now we get this situation. Okay, we have R, we have linear momentum redrawn. Okay, so this is redrawn. Now when we rotate, okay, position vector towards linear momentum, then what we find? So as I said earlier, when we rotate fingers of right hand, which is pointing along the position vector towards the linear momentum, then the outstretched thumb, okay, then the thumb points along z-axis. So what we find, angular momentum, okay, is pointing along z-axis. So this is to be noted. Okay, so we can write angular momentum, okay, and this way also. We can write angular momentum in vector form in this way, or simply we can write in this way. So what is k cap? It is unit vector acting along z-axis. We know I cap is unit vector acting along x-axis, j cap is unit vector acting along y-axis, and k cap is unit vector acting along z-axis. So this expression, okay, or this expression, okay, or this expression is angular momentum in vector form. Now let us write in magnitude. Okay, in magnitude, since we know angular momentum in this particular, okay, case is acting in z direction, so we have z component of angular momentum, so Lz equals R, okay, the magnitude of position vector, P, the magnitude of linear momentum, and sine theta. So we have this. So let us call it equation 1. And we are going to discuss or interpret the magnitude of angular momentum. So I'm writing, let us interpret the magnitude of angular momentum. Okay. Now, I'm erasing this. Okay. Now let us take or associate, okay, sine theta with r. Then from equation 1 we can write Lz equals r sine theta. I am taking r sine theta inside the bracket, okay, and we have P. Now let's call it equation 2. Now I'm redrawing this figure once again, okay. So we have position vector r. So we have linear momentum, and this angle is theta. This angle is pi minus theta, or 180 degree minus theta. Now let us drop perpendicular from origin to the line of motion. Okay, so we are dropping perpendicular from origin to line of motion. So this length is r perpendicular, because we know particle moves in the direction of P. So the line of motion is this, okay. So this represent, or the direction of linear momentum gives the line of motion. So we have this, or we can simply tell that r perpendicular, this is component of position vector, okay, perpendicular to linear momentum. So we can understand in this way also. Now in this triangle, okay, let us find sine pi minus theta, okay. So this is perpendicular, okay. We know sine equals perpendicular by hypotenuse. So perpendicular is r perpendicular by hypotenuse, and hypotenuse is the length of the position vector, so the magnitude of position vector. So we can write r perpendicular is r times sine pi minus theta. So we can write r perpendicular is r sine theta. Therefore from equation 2 we can write Lz, sorry, that is z component of angular momentum, equals r perpendicular times the magnitude of linear momentum. So we have this, and we need to note that mathematically or numerically r perpendicular is r times sine theta, and this is perpendicular distance, okay. So what is this? Perpendicular distance between origin and line of P, because linear momentum is acting along this line, okay. So we have this. Clear? Now I'm erasing this, okay. Now I'm erasing this also. Now let us take, okay, sine theta with P. So what we find from equation 1, we write Lz equals r P sine theta, and I'm keeping P sine theta, okay, inside the bracket. So let me write in this way, okay, P sine theta. So we have this. Let us call it equation 3. Now let us understand equation 3, okay. So I'm drawing over here. This is y and z is directed outward, okay. So this is the same diagram, okay. This angle is theta and this angle is pi minus theta. So it is pi minus theta, okay. This is pi minus theta. Now let us drop perpendicular from the head of linear momentum, okay, to position vector. So this length, okay, is represented by P perpendicular. And what is P perpendicular? This is component of linear momentum perpendicular to position vector. So we have this, okay. Now in this triangle, okay, let us find sine pi minus theta. So this gives me P perpendicular. So this is the perpendicular and hypotenuse is the magnitude of linear momentum. So we have this. Therefore we can write P perpendicular equals P times sine theta. So we get this because we know sine 180 or pi minus theta is sine theta, okay. So this is sine theta. Therefore we can write from equation 3rd Lz equals R times P perpendicular, okay. So we have this. So the z component of angular momentum, okay, is given by R perpendicular P, or we can write Lz equals R times P perpendicular. So this is to be noted, okay.